Continuing our discussion of entropy and Gibbs free energy, let's remind ourselves what standard state is. So for a gas, standard state would be 1 atmosphere pressure of the pure gas. For a liquid or a solid, it would be the most stable form that the material takes at 1 atmosphere of pressure and usually 25 degrees Celsius, whatever the temperature of interest is, but it's always 25. And for a solution, it would be 1 molar concentration of all reactants and products. That would be the standard state conditions. Remember from thermochemistry that we can find the enthalpy change associated with a reaction if we know about the heats of formation of the products and the reactants. So we're just going to sum up the heats of formation of the products, and the N subscript P is the number of moles, and that would just be whatever the coefficient is in the balanced chemical equation times the heat of formation of whatever that product is. And then we have a minus sign and then a big old parenthesis with the heats of formation for all the reactants. So products minus reactants for heats of formation will give us the enthalpy change associated with a reaction. We can do the same thing for entropy. So the entropy change associated with a reaction under standard conditions, that's what the little circle is for standard conditions, is the sum of the entropy of the products times any coefficient for number of moles minus the sum of the entropy of the reactants times the coefficients for number of moles. Notice that these are not the changes of entropy. That is just the entropy of the products and the entropy of the reactants. These are tabulated values. Be careful about units because the entropies are with joules per Kelvin, or joules per mole Kelvin, and the enthalpy are kilojoules. So you always want to really watch units for everything in thermodynamics there. So the reason that we don't have deltas for the entropies is because of the third law. The third law of thermodynamics, we're up to number 3 now, says that the entropy of a perfect crystal at 0 Kelvin, at absolute zero, is in fact 0. So that means that there is such a thing as 0 entropy, and we know what that is. It would be a perfect crystal at 0 Kelvin. A couple things on the trends here. Some of these you already know. The entropy of a gas would be greater than the entropy of a liquid, greater than the entropy of a solid for the same material. And that's because for a gas, there's just more ways that those gas particles can be arranged. There's more ways they can be arranged. The entropy of neon, for instance, is greater than the entropy of helium, and that's because neon is bigger. There's more subatomic particles. There's more space that it takes up. So there's more ways that those particles can be arranged in space. And in general, the entropy of a molecule would be greater than the entropy of an element. Again, it's larger, it's just physically larger, and also there's more moving parts to it. There's more atoms involved, and so they can be... There's twisting and there's turning and there's more ways that things can be moving and arranged in space, so therefore more entropy for a molecule. And in general, the more complicated the molecule, the higher the entropy. You'll see some of those trends as you look up the values in the back of the book for those. A couple of notes. Remember that the heats of formation can be 0. In fact, that is the definition of... that is, by definition, the heat of formation for an element in the state that it's found in nature is 0. Entropy is not 0. We do not have any entropies in the back of the book of 0 because we do not have any perfect crystals at 0 Kelvin. We don't have any perfect crystals. We don't have any 0 Kelvin. So the entropies in the back of the book are not 0. And if we did have perfect crystals at absolute 0, it would be 0, but we don't, so we don't have any numbers that are going to be 0 for entropies. And our Gibbs free energy of formations, those can be 0. As we know, delta G, the Gibbs free energy of a reaction associated with a reaction, determines spontaneity. We have 3 ways that we can calculate. Obviously, it's an important thing to know, right? We want to know whether reactions are spontaneous in the forward direction, spontaneous in the reverse direction, or whether we're at equilibrium. We have 3 ways that we can find that out. One of them is the delta G under standard conditions would be the enthalpy under standard conditions minus T delta S. So delta G equals delta H minus T delta S. Remember for that one that the temperature has to be in Kelvin. And again, watch your units for kilojoules versus joules. The second option is we could do the Gibbs free energy of a reaction the same exact way we did Hess's law. Same thing, you're just going to look them up in the back of the book. That only works though for our tabulated data. You're only going to be able to get the delta G for the situations that are in the back of the book. So 25 Celsius, standard conditions, tabulated data. We can also get that delta G from adding stepwise reactions. So we can do it just like we did Hess's law, where we said if I know something about these 3 reactions or 2 reactions and I add them together to get the reaction that I care about, then I can know about the overall. Because these are state functions, this is the reason that this works. So here's an example. We have N2O plus NO2 making 3NO. And that's the reaction that we care about. We don't know the Gibbs free energy. We don't know whether it's spontaneous or non-spontaneous. So but we are given these 3 reactions. And they obviously have a lot of nitrogens and oxygens in them. And we're given the Gibbs free energy for each of those, again in kilojoules. So I would like to pause here. And then I'd like for you to make an attempt at combining those reactions in a way that will give you the reaction that we are concerned with, which is the N2O plus NO2 yields 3NO. So how can you manipulate those 3 equations that we have information about in order to get the top one? So we'll pause here for just a moment and then restart once you've either finished or gotten to a good stopping point. So when I did this, I labeled the 3 reactions, 1, 2, and 3, so I can kind of analyze them. I'm looking at that and I'm saying number 3, reaction 3, would give me the N2O product. I'm sorry, the N2O reactant that I need. Number 1 would give me the NO2 reactant that I need. And number 2 would give me the NO product. So that's my analysis when I start, is I look at what do I need on the reactant side, what do I need on the product side, which reaction is probably going to be the thing that gives me those. So I'm just going to rewrite those the given information here so that I have a little bit more room. So again, you're looking at the reactions that you know about with the known information and trying to analyze is this going to give me reactant, is this going to give me product, and then what do I need to do to those reactions? Do I need to double things? Do I need to cut things in half? Do I need to reverse reactions? The rules are exactly the same as they are for Hess's law. So if you reverse a reaction, it changes the sign of delta G. If you cut a reaction in half, then it would be half of whatever the delta G value is in kilojoules. So the first thing I'm going to do is cut in half and reverse reaction number 1. So I cut in half a big bracket for the whole reaction, and then when I reverse it, that changes the sign of the reaction. And then I'm going to cut in half number 3. I already has the right things on the right side. I'm just going to cut them in half. And so then that cuts the value of delta G in half. And then number 2, I just have to write as is. And so I just write delta G as is. I'm going to add all these together and just, first I'm just going to rewrite them with cutting all those coefficients in half, just to make sure I don't make any mistakes in distributing that all the way through. And then add them up. And when I do that, I get the reaction that I care about, and the reason that works is because I eliminated, and it's just going to naturally work out that way, of course, if you get them arranged correctly, but I eliminated the things that aren't in my final equation, like the O2s and the N2s. So I've got an O2 on the left, and then a half an O2 and a half an O2 on the right, so those go away. It'd be like an X on the left side of the equation and another X on the right side of the equation. And then I have an N2 on the left and an N2 on the right, and so those go away. I have an NO from the first reaction, and then 2 NO from the last reaction that I wrote on the right side, so that gives me a total of 3. And then to get the delta G for that, I just have to do whatever I said I was doing when I wrote those all out. This is definitely something where you want to not try to do everything in your head, right? You got to write it down. So I do everything, and I get that delta G is 107.1 kilojoules, which is greater than 0, so that would tell me that this is a non-spontaneous reaction in the forward direction as an example problem. And then we have one more thing to discuss, and then we'll have our full arsenal of equations. And that would be how we find delta G for non-standard conditions. So if we have delta G for standard conditions, that would require 1 molar, 1 atmospheric pressure. What would it do if we had something that wasn't that? So delta G reaction without the little circle means non-standard. Delta G with the circle is standard conditions. The Q, of course, is our reaction quotient. R is the 8.31 joules per mole Kelvin version of R. And then temperature, of course, must be in Kelvin so that it's going to work with the units for R. For Q, if it's gases, it's going to be a QP, so you're just going to work in pressures. If it's solutions, molarities, then it's going to be QC, so you're working in molarities. Remember, you're going to, of course, omit solids and liquids for any of those Q expressions. Be very careful with the units. The delta G under standard conditions that you may be given or you may calculate from tabulated data, as we just discussed how to do that, those are going to be in kilojoules. Our R value is in joules. Please make sure that you are watching the units. That is absolutely the most common mistake, is you're trying to add kilojoules and joules. Can't add units if they're not the same. So usually, you could convert either one. Usually people will convert the joules into kilojoules. And you can do that at any point. But the way you don't make those mistakes, you avoid the mistakes, is to write down your units as you're going. And then the whole reason that we'd want to know this about Q, well, one of the reasons, is that then we can relate delta G to K. To our equilibrium constant. So if we have this reaction that says that delta G is delta G under standard conditions plus RT natural log of Q, well, what if we were at equilibrium? If we're at equilibrium, then we know that delta G is 0. If we are at equilibrium, delta G is 0, right? Delta G is negative, means for, spontaneous in the forward. Delta G is positive, spontaneous in the reverse. Delta G is 0 is you're just at equilibrium. So then, if we are in fact at equilibrium and we say delta G is 0, then Q becomes K. That's how those relate to each other, right? Q is the reaction quotient calculated just like equilibrium constant, but under non-equilibrium conditions. So if you are at equilibrium, then Q just becomes K, and you can scooch that equation around a little bit, and you get delta G under standard conditions is negative RT natural log of K. And so that is a way to relate thermodynamics and equilibrium constant, as we will develop further. Thank you very much for your attention.